4.4, absolute maxima and minima. In the past, we've already know how to find the relative or local maxima and minima. Typically, that happens where the slope is 0 or undefined. An absolute maximum or minimum is kind of the same thing. It's just the highest y value on the graph. That could happen at a relative extreme, or it could happen on the endpoints. For example, here our maximum clearly happens where the slope is 0, whereas some graph like this, the absolute maximum is on an endpoint, whereas the absolute minimum is where the slope is 0. Moral of the story, you have to check all of the critical points and the endpoints to find absolute maxima and minima. This slide kind of formally defines maxima and minima, absolute maxima and minima. Here we can see the absolute minimum, no absolute max. No absolute max, no absolute min. Absolute min occurs at two x values, absolute max. No absolute max or min. Notice the difference between B and E. E has endpoints, so E does have an absolute maximum and minimum. They're both on the endpoints. So again, all sorts of things can happen, but they always happen at the critical numbers or the endpoints. The extreme value theorem, it basically tells us that if a function is continuous on a closed interval, then we must have an absolute max or min somewhere. Maximum and minimum somewhere. Think about that. We're on a finite interval, and we're continuous. That means we have endpoints. There's no way to connect 2 points without having a maximum somewhere and a minimum somewhere. Kind of a backup theorem to the extreme value theorem says if the absolute extreme is on an open interval, then it must be at a critical number. Meaning, if you have an absolute max or min on an open interval, it's got to be where the slope is 0 or undefined. So that should sound familiar from what we did in the first few sections of this chapter. Example 1 says find the absolute max and min of this function on the closed interval 1 to 5, meaning I don't care what's happening before 1 or after 5. So step 1, we find the critical points. Again, that's anywhere where the slope is 0 or undefined. This is a polynomial, so the slope's never going to be undefined. We can find out when the slope is 0, though. Just for some practice, I highly recommend you pause the video and try to find these critical numbers on your own, and then check with my work. I get critical numbers x equals 2 and x equals 3. I'm not trying to find out where I have relative min, relative max. I'm not trying to find concave up, concave down. This problem just says find the absolute max and min. So all I really have to do is find out which x value gives us the biggest y value, which gives us the smallest. I have to check 2, I have to check 3, and I have to check the endpoints, which in this case are 1 and 5. Pause the video, make sure you know how to plug those numbers in yourself. Check with my answers. Once we plug these in, it's pretty fast to see which point is the absolute minimum. That's the smallest y value. And which point has the absolute max. Turns out in this particular problem, the minimum and the maximum both occur on the endpoints. That's not what the case always is. Up above, you can see a picture of this graph. You can see that absolute minimum at 1, 23, and the maximum at 5, 55. The other two values, 28 and 27, ended up being places where the slope was 0, but it didn't happen to be the absolute max or absolute min. Same game, we're going to find the absolute extrema of this function on the given interval. And we want to find out where those values occur. So your game plan should be something like this. Define your derivative, set it equal to 0 or undefined. This isn't a polynomial this time, so there might be some places where the slope is undefined. Find all those critical numbers, check them and the endpoints. Wherever your highest y value is, that's your absolute maximum. Wherever your lowest y value is, that's your absolute minimum. Go through those steps, pause the video, see if you get the same results as I do. As soon as you unpause, I'm going to be to the point where you plug in numbers, and then we'll talk about the max and min. One thing I'll point out that might have gotten some of you tripped up, to go from here to here, found a common denominator, so if you got stuck there, go figure that out. And after plugging in all of my critical numbers and my endpoints into the original function, I see that my absolute maximum happens at this guy, and my absolute minimum happens at this guy. Notice I'm not on the endpoints this time. If you want, you could go ahead and find an appropriate viewing window in your graphing calculator and verify this with a graph. This next box tells us some things that, if we stop and think about them, they're kind of common sense. It tells us that if one end of a continuous graph goes up and the other one also goes up, then we must have some absolute minimum somewhere. Similarly, if both ends of the graph go down and it's a continuous graph, then we must have a maximum somewhere. If one end goes up, one end goes down, like in these last two graphs, then we won't have an absolute maximum or minimum anywhere. Again, if you stop and think about those, they kind of just make sense. We obviously still could have relative max and min all over the place. This just tells us stuff about the absolute maximum and absolute minimum. So this next example says, what can you say about the existence of absolute extrema for polynomials? You should be able to tell me something about what happens if the degree is even or odd. And you should also be able to tell me specifically what happens if the leading coefficient is less than 0 or bigger than 0 for both of these. This is an Algebra 2 topic. Just using a calculus word, absolute extreme. You should be able to use what you know about Algebra 2 polynomials and honors pre-cal and tell me what you know about absolute extremes on both of these. For instance, if we have an even degree with a leading coefficient less than 0, we know that both ends are going to go down. So what are we going to have? A maximum. Somewhere. We don't know where it is, but we know there's going to be one. Try to put the word max or min. It should actually be absolute max or min. For the other three, pause the video, see if you get the same answer as I did. On your even degree polynomials, you have kind of the same situation as this guy, but flipped upside down, so you get an absolute minimum. Odd degrees either have arrows going up and down like this, or the reverse. Either way, you're not going to have any absolute extrema. Example 4 says, determine by inspection whether this function has any absolute extrema. If so, find them and state where they occur. Before we even do any calculus, we should be able to look at this and decide if it does in fact have absolute extrema. This is a polynomial, even degree, leading coefficient bigger than 0. We should know what that means without looking at the graph to the right. We should know that both arrows are going to go up. So we'll have a point somewhere at the bottom, and that's our absolute minimum. So we have to figure out where it is. It can't be on the endpoints because this goes on forever in both directions. So it must be at a critical number. So we've got to find our critical numbers, set them equal to 0, find the critical numbers, plug them into the original, and find the absolute minimums. Go ahead and try that on your own and see if you get the same thing I did. Using the fact that we know that there has to be an absolute minimum and that the lowest point on this graph is at -1, this must be our absolute minimum. It's worth noting that this is not an absolute maximum because our previous analysis told us that the graph goes up forever. So there is no absolute maximum. There's only an absolute minimum. Now you can look over to the graph to the right and you'll notice that this kind of follows from what we just found out, the absolute minimum at -1, -1, whereas 0, 0, the slope was 0, but that was not a maximum. It wasn't even a relative maximum or minimum. This box is filled with a little bit more common sense after you stop and think about it. Reading the words on here don't seem like common sense, but the ideas behind it do. We're dealing with open intervals now where we have an asymptote. If we go up on both ends, on both sides of that asymptote, then we must have a minimum somewhere, absolute minimum. Same idea, if both asymptotes go down on that open interval, we must have a maximum. If one goes down, one goes up, no absolute maximum, no absolute minimum. Very similar to the last box where I explained kind of the same thing. If you look over this for a minute, this should seem like common sense. It's not something you should have to memorize. Okay, this next example tells us to determine whether the function has any absolute extrema on the intervals 0 to 1. Let's figure out what's happening at 0 and 1. Since we're not including 0 and 1, by the way, notice if we tried to include 0, we'd get undefined. If we tried to include 1, we'd get undefined. This is a rational function. That means we have asymptotes at these points. It's possible to get holes also where a function is undefined, but nothing cancels from the top. So using our pre-calculus analysis, we should be okay with the idea that these are asymptotes. So let's find out what's going on near those asymptotes. First I'll factor the bottom, and we'll look at what's going on the left-hand side of the interval. We're going to approach 0 from the right, and we end up with something like 1 over a tiny negative, which to me sounds like negative infinity. Let's figure out what's going on the other endpoint. Notice if I get another negative infinity, that means both ends of this graph go down, so I'll have a maximum. If my next limit gets an up arrow, I won't have any absolute maximum or minimum because one end will go down, one will go up. I can tell from the picture which one I'm going to get, but we should be thinking about this stuff because, as you know, you will not have a picture in front of you every time. So we want to look at one from the left. Looks like we get 1 over 1 times a tiny negative, which sounds like negative infinity. So we do have the situation where both ends of the graph go down on the endpoints. They're not really endpoints because we don't actually touch. We have asymptotes. So we must have a maximum somewhere in between those two asymptotes because the function is continuous everywhere else. So to find that, we have to find out the critical numbers of the original function. So let's put that on another page and on your own try finding the critical numbers of this function and finding out where that maximum occurs. Remember, you only care about numbers between 0 and 1. Looking at my first derivative, I find 3 critical numbers, one at 1/2, one at 0, and one at 1. Immediately I get to cross off 0 and 1. because they're not in my closed interval. Remember, our interval is 0 to 1, non-inclusive. So I could really only possibly have my absolute maximum right at 1/2. So we could just figure out where f of 1/2 happens to be and verify on your own if you wish, but that happens at -4. We know from our analysis that must be an absolute maximum, and we know that because at the asymptotes both arrows went down, so somewhere in the middle we have a maximum at 1/2, -4. I'm going to go back to that previous slide, and we can look at the graph and verify this. Both endpoints, both asymptotes went down, and at 1/2 we had our maximum, and that's at 1/2, -4. Everything seems to work out. Our last theorem of this section. Off the top of my head, I can't think of when this theorem is super useful, but basically what it says, if a function has one relative minimum only, then it must be the absolute minimum. If a function has, rewind, this theorem's only true if there's exactly one extreme on an interval. If there's more than one extreme on the interval, then this theorem means nothing. And if that one extreme is a minimum, it must be the absolute minimum. If that one extreme is a maximum, it must be the absolute maximum. Again, I can't think of a time when this is super useful to know off the top of my head, but I am prone to making mistakes, so maybe it's useful. This last example says find the absolute extreme, if any, of this function on the interval 0 to infinity, not including 0. So we should figure out what's going on in this function on the ends. Since we're not including 0, we should find out what's happening slightly to the right of 0. Looking at that, it looks like I get something close to e to the 0, which is 1. So my graph gets close to 1. And I can see that on my picture to the right. I should also find out what's happening as x gets really, really big. And by inspection, we can tell real fast this is going to get to be a huge number, e to the infinity minus infinity, but the x cubed infinity wins, so this is really e to the infinity, which is infinity. It means it gets bigger forever. And we can see that on our graph too. Now we're going to look for any critical numbers to find out places where the slope of this might be 0. I can tell we're not going to have an absolute maximum. We should know that because the arrow's pointing up on the far right, so it's going to get bigger and bigger. No absolute minimum. We might have an absolute minimum, no max. The way we find that is we look for critical numbers. By the way, this little 1 is going to kind of mess us up. I can see on the graph that it's going to go down, but all I really know so far is I have an open circle here and an up arrow there. On your quiz or test, you're not going to have a picture of the graph to look at as you're going to do this. So our graph might do something like that. You should ask yourself, does this have an absolute minimum if my graph looks like this? And the answer is no. The graph gets close to 1 but never touches. So if something like that happens, we would have to say no absolute minimum. I know it's not going to end up looking like that because I can see the graph above, but you need to be thinking about this kind of stuff. Let's find our critical numbers. On your own, pause the video and find your critical numbers. At that point, plug your critical numbers into the original function. And we'll see if we get the same results. Hopefully you got the same critical numbers as I did. A couple things of note. E to something never equals 0. That's why I didn't pay attention to that. You should be able to tell me why I crossed out x equals 0. I didn't even bother testing it. There's a legitimate reason for that. And I plug in my x equals 2. I get 0.0183. Going back to what I know about this graph, I have an open circle at 1 and an up arrow on the right. I just found out that at e to the negative, or actually at x equals 2, I get a number smaller than 1 on my graph. Therefore, since that's the only other place where we found a critical number, this must be an absolute minimum. And this actually does relate back to that theorem that I said is kind of useless from the previous slide. It says that, once again, let's look at what that theorem says. It says, suppose we have only one relative extreme, which we do in this case. It was at x equals 2. If that's a relative minimum, which it is, then it must be the absolute minimum. I still claim this theorem isn't super useful for this problem because logic dictates that we're going to just come up with the same conclusion. And here's my logic. One end goes up forever. No absolute maximum. The other end gets close to 1 but doesn't touch. So that can't be an absolute maximum or minimum. The only way I'm going to get to my other critical number is if that critical number is the absolute minimum. Because if I went lower than that, I'd have to have another critical number, and I don't. Moral of the story, this is an absolute minimum. So we can kind of sketch the graph. My graph doesn't look quite as accurate as that one because it flattens out a lot around 2. But it is what it is. All the important information is in this graph. Absolute minimum, end behavior, open circles, increasing, decreasing. We might be worth checking into concavity if you were asked to. That would be more work. We can get the second derivative. That's it. At this point, pause the video or open your book and do the problems on page 272. Have a wonderful day.